Assalamu alaikum. In today's lecture, before we're gonna start the today's lecture, I was gonna let you know that we were talking about autocorrelation function of a White's and stationary random process in our previous lectures. So we're gonna discuss some of its properties and some of its mathematical definitions as far as the autocorrelation function of a random process is White's and stationary random process is concerned. So for a White's and stationary random process. The autocorrelation function is only a function of the time difference. That is the tau that we were talking about in previous lecture, that tau will be equal to t1 minus t2. Remember these are the two time differences here as far as random variable is random process is concerned, and it's going to be defined like rx of tau here. That will be the expected value of a random variable into the x of t, and we are taking and multiplying this value with an random variable when we are taking it t plus tau, where tau is t1 minus 2 t2. You can say this tau will be the difference between the two time intervals, and that will going to be taken for minus infinity to positive infinity. Now the properties of as far as random autocorrelation function of a real valued White stationary process is concerned, first property is that the autocorrelation function in White stationary process is symmetrical. That is that r, when we're going to find rx of tau, that will be equal to rx of minus tau. Okay, symmetrical in tau about 0 here. Okay, and second property is that rx of tau is less than or equal to rx of 0 for all tau. Maximum value occur at the origin here. For any value of tau, that will be less than or equal to when we are having a autocorrelation function at 0. When I'm going to describe the you can say graphical representation of the autocorrelation function of different random variable, then you will come to this property, then you will know this property here. Okay, first till now you have to remember this property, that autocorrelation function at any value of tau is less than or equal to autocorrelation function at the value at 0 here. And the third property is that the autocorrelation function tau will be, you can say, uh, in time domain will be, you can say it is called a free powered specular density in Fourier transform. This is the third property. And the fourth property is that when you're going to find autocorrelation function at 0 of a White stationary random process, that will be equal to the average power of the signal here. So these are very four easy properties as for the autocorrelation function are concerned. Then moving further, we're gonna see some more definitions, and this is the definition that we're gonna use in when we're gonna having an analysis of our random processes in communication system, and this is called time averaging and ergodicity. When a random process belongs to a special case known as an ergodic random process, its time average equal its ensemble averages. Remember from the previous lecture what is a time average and what is an ensemble average. So as far as ergodic process is concerned, its time average is equal to its ensemble averages. Okay, this is a special case of a random process known if this is equal, if both averages, time averages and ensemble averages are concerned, that is called an ergodic random process. The statistical properties of such processes can be determined by time averaging over a single sample function of the process. If we have this thing, then the statistical properties of such processes can be determined by time averaging over a single sample function of the process, because both ensemble and time average are same. So we're going to only you can say the statistical properties of that random variable can be defined only by time averaging over a sample function here. A random process is ergodic in the mean if mean is equal to limit t approaches t 1 over t minus t by 2 to t of t x of t. If this condition holds in a random process, that is called a random process is ergodic in the mean. Okay, uh, it is also a random process is ergodic in the autocorrelation function if the mathematical expression holds for this mathematical expression that is highlighted here is hold as far as the autocorrelation function is concerned. Okay, now moving further, uh, again we're going to talk about some more thing, and that is called the power spectral density and the relationship of the autocorrelation function. Remember, a random process x of t can generally be classified as a power signal having a power spectral density that is called gx of f in frequency domain. The principal feature of the power spectral density are given below. I'm going to start from the first point, and that is called the power spectral density of a random variable is greater than or equal to 0. It means that it is always a real valued, and it will be it will start from 0 and go to the positive values. Second point is that the power spectral density will be equal to g x of f will be equal to g x of minus f. That is that for x of t real valued, power spectral density function will hold this second condition here. And as far as third point is concerned, the power spectral density function uh, will be, you can say, will gonna represent a autocorrelation function in time domain. So they are both the transformation pairs as far as time domain or frequency domain is concerned. For example, if we have a autocorrelation function, if we have a value of autocorrelation function in time domain, then we can find the its power spectral density for in frequency domain. As next point is that the power spec this is the last point here. This is it, that the p of x will be minus infinity to infinity gx of f divided. What this integration will tell us, it tells us the relationship between average in normalized power and psd here. This is the psd, this is the power spectral density function in frequency domain, and that is the power that we are calculating from this. By integrating this power spectral density from starting from minus infinity to infinity, we'll get the power. That's the relationship between power and power spectral density function here. So that's about the power spectral density. And then we're gonna I will gonna show you some uh, sorry, I will going to show you some, you can say, graphical representations as far as these mathematical representations that we have studied so far. Here you see a random binary sequence, and that is represented with x of t here, and that's, for example, that's a binary sequence here, starting from -1, 0, and 1 here. It's the value at this point. You can say at the axis is 0 here, and we have the a negative value as -1 because we have our binary sequence here, and 1 plus 1 for the positive pulse here. And we're going to see this one is a DC value here. Then if you're going to find xt minus tau 1 here, that will be equal to, you can see there is a delay here, and that is called a tau here. So this will be equal to t minus tau 1. And you know from the definition of our course in signal system that this will be a right shift here, and we are providing a right shift here. Then uh, now see here, using this one, if you're going to find the autocorrelation function, that will be equal to this relation that is given here, and that's going to look like this here. Okay, and in this case the DC power will like going to lie here. Okay, so that's about the graphical representation of some of the autocorrelation function, and as far as delay, as far as the time differences in respect of a tau here, and the random binary sequence here. Okay, fourth one, here we are describing some of the um, property of a autocorrelation function. Here you have seen this is the autocorrelation function as far as tau is confirmed between two time averages. That will be equal to 1 minus mod of tau over t for tau less than t here. You can see here, and 0 for tau greater than mod of tau greater than t. You see elsewhere it's 0 here. Now this one is I was talking about earlier on, that Rx of 0 going to be found here, and this will be Rx tau 1 and so on here. And that will be, if we are taking Rx of 0 here from this autocorrelation function that is given here, that will be the total average power here. Okay. Now again, moving further, you see here that, for example, I told you that if the PSD is given here, and then the PSD will be represent a autocorrelation function in time domain. So for example, if we have a PSD here of a rect function, that it's going to be defined with the sync function here. And you know from the Fourier transform pair that that will be equal to this one. This is from the Fourier transformation here, and we're going to define this one like this here. And remember, this one here is the total average power here, this from the main lobe here. Okay, if you're going to take gx of f here for this area, that will be give you the total average power here. So that will be the fourth property that we were talking about. Now moving further, we're gonna I'm gonna show you some more things as well. uh, Here you see this one. For example, Here we have, earlier on we have this T1, then we have made a delay here, we have a binary sequence here, then we have a made a delay here, then we have defined a autocorrelation function here, and then we have defined this, you can say the autocorrelation function, and then we have defined this power spectral density, or the we have taken the total average power. Now see here, we have a random binary sequence here, and that's the time we are taking here. And this is again, the random binary sequence is going to be have a minimum value -1, middle value 0, and then we have a +1 here, and that is a high bit rate here. Then see here, if we want to find xt minus tau1, that will be a delay here. And then again, if you're going to find rx tau1, that you're going to find it using this mathematical expression, or you can find using this graphical representation. And when you're going to find the, if you want to find rx tau here, that will be equal to this one. Remember, this is the binary sequence, sorry, this is, and that will be the autocorrelation function for that binary sequence here. And if you want to see its power spectral density function, that will be equal to this one, because now in this case, we are having this thing here. So that's how you're gonna see different things like autocorrelation function, power spectral density, as far as any binary sequence pulses are concerned here in digital communication. Okay, now moving further, I'm going to show you what is about the noise as far as communication systems are concerned. The term noise refers to unwanted electrical signals that are always present in electrical systems. For example, spark plug ignition, noise, switching transient. Uh, sorry, I was going to zoom is less. Switching transients and other radiating electromagnetic signals or atmosphere, the sun, and other galactic sources here, that we're gonna call a noise as far as communication systems is concerned. And noise is called a unwanted electrical signal in communication system. Now, this noise and communication system can describe thermal noise as a zero mean Gaussian random process here. A Gaussian process n of t is a random function whose amplitude at any arbitrary time t is statistically characterized by the Gaussian probability density function here. And a Gaussian process n of t is a random function. Please remember that we are describing thermal noise as a zero mean Gaussian random process. Then we are defining a Gaussian process n of t is a random function, and this random process is going to be characterized by the Gaussian probability density function that is given here. Here, this one. Okay, that will be equal to p of n 1 over sigma under root 2 pi exponential of -1/2 n over sigma square here. Now, again, moving further, when you're going to see the normalized or standard Gaussian density function of a zero mean process, and then it is obtained by assuming unit variance and central limit theorem. And we're going to describe this graphically using this mathematical expression that we have decided earlier. Remember, we have described this zero mean process with the help of a Gaussian random process here, and using the you can say this mathematical expression that we have discussed earlier, that one, that's the Gaussian probability density function. We have described this thing here. This value will be 0.399 when you're going to move when we have putting a different value of sigma here, and this sigma is 1 here. We get this 0.39, then we have 0.3. This will be a this will be called a sigma here. This will be one. So because we are taking sigma is equal to 1 here, so that will be called normalized Gaussian probability density function here. Okay. Now I'm gonna show you more thing. There is another thing that is called white noise, as far as the noise in communication system is concerned. Now, what is a white noise? The primary spectral characteristic of a thermal noise is that its power spectral density is the same for all frequencies of interest in known communication system. Now, the power spectral density is given like this one. The power spectral density is given like this one, and that will be n naught over 2, where n naught is the power, and that will be 2. And then we're gonna the unit of that n naught over 2, the power spectral density will be watts per hertz here. The autocorrelation function of white noise is uncorrelated here. For example, if we have an autocorrelation function here, we draw here. Remember, if we're going to take the inverse of that power spectral density function, that will be equal to n over 2 impulse of t here. Okay, the average power of a white noise is infinite here, and here you see the power we are finding from a power spectral density function, and that is given here, this one. Putting the value of g n of f as n by 2 here, we are taking this one as infinity. So if you're going to plot this power, then it's going to look like this. GNF gonna look like this, is a straight line starting from minus infinity to positive. This is called an infinite here, infinity here. And if you're gonna represent it in terms of autocorrelation function, that will be a delta function with an amplitude and naught by 2 here. Okay, now the effect on the detection process of a channel with adaptive wide Gaussian noise is that the noise affects each transmitted symbol independently. Such a channel is called memoryless channel here. The term additive noise, that the noise is simply superimposed or added to the signal here. Uh, Now, there is one more topic that is called signal transmission through linear systems, but I have already gone through this topic in a course of in course communication system. So you can see this thing when you're gonna see the lectures or video lectures from the chapter 3 of the book, or chapter 3 of the book, Modern Digital and Analog Communication System, in communication system course. So you can see this thing, the signal transmission through linear system, from your from the previous lectures as well. So till then, goodbye. And as far as this noise analysis is concerned, you're gonna use this noise analysis mostly, that the function I have described you here, in mostly in your lab work. And as far as its numerical portions are concerned, we're going to discuss this noise analysis, uh, and the definitions of the random process that we have discussed in these two lectures in our interactive session. So thank you so much.